Today we'll talk about irrational number. Now what we learned in last lecture that there are lots of rational number between these whole number, like between 0 and 1 you could have many rational number. And what you realize that, and similarly the case here as well, these are all places for rational number. Now the question arises, are there any more number left? The answer is yes. There are certain numbers which are called irrational number and they cannot be expressed in the form of P by Q where Q is equal to 0. Are these numbers, do they exist? Yes. And we'll shortly see why and what kind of numbers they are. So let's take an example of a right angle triangle where one side is 1 and if I draw another side which is also 1 and yes. Now using Pythagoras theorem, if I want to find out what is the length of AC, that we know is under root 2. Now this number under root 2 is irrational number. Why? Because there is no way we can represent under root 2 in form of P by Q. Are there more numbers like this? There are plenty of numbers like this. Another example, common example is a number pi. And again it's very interesting to know these irrational numbers somehow exist in the nature. And why pi is something which exists in nature? Because if I take a circle and a radius of circle let's say is 1, the area of this circle would be pi into 1 square, which is pi. So what it means, the nature actually provides some kind of irrational number. Let's take another example. Suppose there is a cube, right? Let me draw this cube here. And if you have been asked to find out what is the length of, it's a diagonal, right? This line. And let me put this line, denote this line with red. Yes. Now suppose you have been asked to find out length of this line, which I can denote, let's say AB. This, as we know, I can draw another line here. We know this is, suppose the side of this cube is 1, this is also 1. This length would be root 2, and using Pythagoras theorem we can find out this length AB would be equal to root 3. Okay, how we did that? Because root 2 square plus this side is 1 square. Okay, and I took under root of that. So that's a root 3. So what is it telling? There are many irrational numbers which exist again on this number line, and nature has provided us a lot of evidence of irrational number. In fact, there is a very interesting story about it, that Pythagoras had a disciple who found out about irrational number root 2, and he met a very bad end because he had been thrown into river because people were shocked that there is something called irrational number, and probably they didn't want to tell everyone about it because those days going against accepted belief was probably a crime. So now suppose we need to represent this irrational number on the number line. How do I do that? Well, one of the simplest ways is, suppose you want to represent root 2. So let's say this line is, we can draw, which is 1, and I can draw another line up which is also size 1, and this hypotenuse of this triangle, this line is actually root 2. Now how do I draw this line here? All I have to do is just take this as a center and draw a circle, okay, like this. wherever this line intersect the line number line, that becomes root 2. So your root 2 would be somewhere. Okay, now can we represent root 3 also on the number line? Yes, it is possible. Let's see how we go about doing it. Suppose this is number line and this is 0 and this is 1. And let me just extend this line further, and this is 2 and this is 3. So what we did first, let's first make root 2, and let me just draw root, extend this a little further, and this is root 2, and if I take a circle with center at 0, this circle will intersect number line here, and this is root 2. Okay, we are clear till this point. Now let's try drawing making root 3. So what I'll do is I will just draw length 1 here, and this line now would be this is root 2, this is 1, so this would be root 3. And what I'll do is, let me take, again I'll take center at 0 and draw this, and this is where this arc is intersecting number line. This would become root 3. You could same way go ahead and make root 4, root 5, root 6, and they all can be represented on number line. This is way how you go about making irrational number. Now there is something, another very interesting fact is there. You could say all rational number. Now let's see decimal form of, let's see irrational number in decimal form, how they look like. Let's take most famous of them all, which is pi. How does it look like in decimal form? It is written as 3.141592, and it can go on forever. Notice one thing, there is no termination. Okay, and there is no repetition. What we saw in case of rational number. So this is very unique property of irrational number, that in decimal form they will not terminate and they will not repeat. Take another example, which is root 2. What happens? Root 2 again 1.414213, and I have written just few digits, and after that again it is similar property. So there is no termination, no repetition, and they cannot be represented in form of p by q. Okay, this is the property of irrational number, and there can be large number of irrational number. In fact, irrational number, there can be infinite number of irrational number. Let's take another example. Suppose you have a rational number which is let's write 0.2, and let's say there is another rational number which is 0.3, and if I want to draw it on the line, here is 0.2, here is 0.3. How many irrational number would be in between these two? The answer is infinity. Why? Let's see how we can do that. We can always write 0.2, 1, 2, 3, 4, 5, 6, and it can go on till infinity. This is one number. Again you can write 0.21, 1, and again you can start 2, 3, 4, 5, 6, and go on up to infinity. And like that we can just continue this series You can make it another 1, 2, 1, 2, and again you can start 1, 2, 3, 4, 5, 6, like this. And you can actually dream of infinite number of irrational number between any two rational number. So irrational number is also a very large group of number which can extend up to infinity. In fact, it does extend up to infinity. Now let's see what are the real numbers. So if we draw this number line and we have all possible number on this, all negative and positive numbers up to infinity, up to minus infinity, all number on the real on this number line, all numbers, and they can be rational or irrational. They all are put together, they are real number. Okay, so this number line represents only real number, and real number as a group, they contain within them natural number, which was represented by n, whole number which had 0 in it, integers, and all the, as I said, rational number and even irrational number. So the question, if I ask you in reverse, are all irrational number real number? The answer is yes. All rational number are real number? Yes. All integers are real number? Yes. And similarly, all natural number and whole numbers are also a real number. But if I ask you reverse question, all real numbers are integer? No. Why? Because there can be non-integer real numbers also. Same way, if I ask you a question, all real numbers are irrational? The answer is no. Why? Because there are other numbers apart from irrational number, which basically means rational number, and they are also part of number line, and they exist beyond irrational number.